Today we're revisiting a cold case, but maybe not the kind you're thinking of. We're looking at a neurological data set.
From 2014, right.
That's the one. And for a whole decade, researchers thought they'd squeezed every last drop of information out of this data, which came from macaque monkeys.
Until a team from MIT and Dartmouth took another look. And they used a new kind of tool, and, well, they found something huge hiding in plain sight.
It's a fantastic example of how just having the right tool can completely rewrite what we know.
It is. So for this deep dive, we're looking at a study in Nature Communications from Dr. Earl Miller's lab. And the key wasn't, a bitter microscope. It was a zero-trained computer model.
And that term zero-trained is really the crux of it, isn't it?
It is.
We're not talking about a typical AI like a large language model that just reads the internet.
No, not at all. This is more structural. They used a platform, I think it's called NeuroBlocks. The researchers basically built a model from the ground up using raw biological equations.
So they coded the literal laws of the brain's corticostriatal circuit, the part that does planning and memory.
Exactly. They coded the rules and then just hit run.
So instead of teaching it, they just built a digital brain circuit and let it be a brain.
Precisely. And when they gave this model the same task the monkeys did back in 2014, categorizing dot patterns, the results were kind of eerie. The model started producing these electrical signals, these spikes and waves, that were basically identical to the real monkeys' brains.
Wow.
But then it did something that at first just looked like a bug, a glitch in the system.
Which was?
A whole group of neurons started firing really consistently for the wrong answer.
And normally you'd expect those to just fade out as the model learns.
Right.
You prune the errors.
Right. But here, the signals for the incorrect choice got stronger, right alongside the correct ones.
That's the anomaly.
That's the one. They called them incongruent neurons, or ICNs, and when they saw this in the model, they went back to that original 2014 monkey data.
And let me guess.
They were there the whole time. The first team had just filtered them out, assuming it was all just noise.
That is incredible. But it feels so counterintuitive. Why would the brain spend energy actively predicting the wrong answer?
Miller's theory is all about cognitive flexibility. If your brain optimizes 100% for the right answer, you become rigid. You can't adapt if the rules suddenly change.
Ah, like the analogy they use of driving to work.
Exactly. You have your main route, but you don't just delete all knowledge of the side streets from your memory. You keep them, just in case.
That connects perfectly to a message we got from a listener, Elton. He made this point about evolution and how knowing the wrong answer can be even more important than knowing the right one.
Oh, how so?
Well, he used this amazing analogy of standing at the edge of a cliff. You want to get to the valley below. Finding the right path down is good. But knowing the wrong answer, which is don't just walk off the edge, is, way more critical for your survival.
That is a brilliant way to put it. It reframes the whole thing. Pruning the wrong answer in that case is fatal. These ICNs could be the very mechanism that keeps that do not do this signal alive and active.
So they're like a library of dangerous or not right now options that you keep loaded in memory.
That seems to be the idea. And this isn't just theory, it has some really immediate applications. The fact that the NeuroBlocks model predicted this biological fact so well is huge.
Because it proves the model really behaves like a brain.
Yes, so now you can test neurological drugs on a computer circuit before you ever get to animals or people. It's faster, safer, way more precise.
And it could change how we understand things like Parkinson's or schizophrenia.
Absolutely. Those disorders involve this same circuit. If your ICNs, your wrong options, are too weak, you might get the kind of rigidity you see in Parkinson's.
And if they're too active.
You might struggle to tell the right answer from the wrong one, which could be related to the cognitive confusion in schizophrenia.
It's just a fundamental shift. We thought the brain wanted to be efficient, but maybe it just wants to be resilient.
And it does that by keeping its options open.
Which brings me back to Elton's point, and it makes me think about standardized tests, of all things.
Okay.
He mentioned that we spend so much time drilling kids on finding the one correct answer. We might be ignoring the value of knowing why the other answers are wrong.
That's a really valid concern. If our brains are literally wired to value these wrong answers for flexibility, maybe our education system is, in a way, fighting our biology.
Exactly. So it really leaves you wondering, doesn't it? Are we spending too much time teaching kids to find the right answer and not nearly enough time teaching them how to recognize and analyze the wrong ones?
We might be accidentally training out the very thing that allows for creative, flexible problem solving later on.
It's a lot to think about. And this whole discovery only happened because a computer model did something a human researcher dismissed as an error. So the question we leave you with is this: how much other knowledge is just sitting there in old data sets, waiting for a machine to look at it in a way we haven't thought of yet?